Okay. Your homework from last night, I got it graded, I don't have it in the book though. So we'll do it in the grade book.
I'm
And
doing it right now.
we'll be good. What about last night's homework?
22.
Remind me what section we're in, Kramer?
50.
50.
I think it's 1.
Yeah, I got A too, I just didn't get B.
You got 8?
No, A, like part A.
Oh,
Thank you.
I'm assuming that there was
Kramer, did you have a question with both A and B?
1. I got a question with B.
Okay, so, not a question with A.
No.
Does anyone else have a question with A? Sweet. So B says 4 log base 5 of 3 minus log base 5 of x equals 0. Oh my gosh. Well, as you look at these things, we're trying to make this simpler to process. So is there anything that we can do looking at this, using our log rules, you think, that can make this simpler to process?
You take the 4 over 3.
Perfect, okay, that's a good first step. So now we've got something to work with. And 3 to the 4th, if you even wanted to, you could just write 81. Now, boy, anything else?
You could do it like divide over it.
You could divide, right, because you have logs that are subtracted. So we subtract exponents when we divide the numbers. So we could go log base 5 of 81 over x equals 0. That would work. Now what do we want to do? When we just have the log on the one side, what could we do? Do you like logs, Kramer? Do you prefer logs to not logs? You do. You'd rather see logs than no logs.
I don't know why it's here.
Okay, well that's fine, but at this point, I think we can get out of log form. 5 to the 0 power is this. 5 to the 0 power is 1. Cross multiply.
Oh, that's what I forgot to do.
Because if 1 is 81 over x, oh, think about this, Kramer. Watch. This is where we were at.
Yeah.
Look at that for 2 seconds. 2 full seconds. X has to be 81.
Yep.
Because for a fraction to be 1, it's got to be something over itself.
Yep.
Did anybody do this a different way? Let me ask this question. Did anybody do this problem a different way? Watch this. When we had this here with these 2 logs, check this out. And the 0 on the other side, it's algebra. I can just add this guy to the other side. Log 5 of 81 equals log 5 of x. Now, that takes mathematical foresight. That takes training. That takes whatever. But all I'm showing you is if you don't break the rules, if you play the algebra game, if you play the log game, if you play the math game, and you know the rules of the math game, you can get the answer multiple ways in a lot of cases. Some cases, there's only one way to get to the answer, but in a lot of cases, there are multiple ways. And sometimes, some ways, you like, oh gosh, why didn't I see that? And then other times, you go through the whole thing, but you know what? Guess what? Both ways, x equals 81. What's wrong with that? Nothing, because that's the right answer. So, we move on. Any other questions? I take silence as a no or yes?
For number 16, I understand the sine graphs.
Yes.
The cosine graphs. I get a little confused.
Okay? Now, the difference between a sine graph and a cosine graph is just what it looks like. Because the sine graph starts at the origin that's the sine graph, starts at the origin, and the cosine graph starts up at 1. That's the main difference. So when I think of the difference between a sine and a cosine graph, I think sine of 0 is 0, cosine of 0 is 1. That's the difference in starting point. But they look the same. Now, so 16 involves a cosine graph. Let me try to replicate what is in 16. The high point is 40. The low point is -10. And you can actually see, they tell you what the center point is. The center point is 15. They tell you where that center line is. That means we've been shifted, right? Now, we also notice that this graph starts, rather than up, this graph starts down. It goes like this. And over here, we'd be at -360. Because every time we go 360 degrees, we've recycled ourselves around the unit circle, literally. Okay, so is this a regular cosine graph? Certainly not. No, number one, what are the differences between this cosine graph and that cosine graph? Let's start listing the differences. What are the differences? One difference between the regular cosine graph and this graph. It starts in the negative. So what does that mean? Let's just write that down. It starts in the negatives, which basically means everywhere where the original one was positive, this one's negative. Everywhere where the original one was negative, this one's positive. That tells me something. That means I'm multiplying by a negative. So this is a negative cosine graph versus a cosine graph. Okay, what else is different between the regular cosine graph and the cosine graph we encounter?
Oh, it's at 40 and -10.
Okay, so normally the peaks are 1 tall. How tall are the peaks here? 25. So we have peaks of 25. So rather than going up 1 and down 1, we go up 25 and down 25. What's that? How is that caused? That's caused by somebody else chime in here. Rather than going up 1, we're going up 25. What causes us to have these bigger peaks, these more extreme peaks? What happens to our sine graph to do that? This is good that we're going over this, because this is something that's not perfectly understood. Now, when I look at my XY table, somewhere along the way, I get a y of 1. Somewhere along the way, I get a y of -1. Because I go up to 1 and down to -1, right? Now, if I wanted to go, rather than going up 1, if I wanted to go up 25, what would I have to do? I could just multiply by 25. 25 cosines. So peaks of 25 means that I'm multiplying by 25. What else is different? In addition to it starting in the negatives, meaning we multiply by a negative, in addition to the peaks being 25, meaning we multiply by 25, what else is different? There's one more thing that's different. The normal cosine graph is centered at, yeah, Jordan?
Let's shift it up to
Yeah, the normal cosine graph is centered at 0. This one is centered at 15, so the center line is at 15. That means it's shifted up 15 units. So let's put this all together. We are different from a regular cosine graph. How are we different? We need to multiply by a negative, we need to multiply by 25, we just shift it up 15. So, here's multiplying by the negative, here's multiplying by 25. And to take everything and shift it up 15, right? I could take this value, and if I wanted to shift it up 15, I just do that to it, right? So I'll just do the same thing here. I got this value. Boom. I just made it 15 units higher. These three pieces of information at this point are the three pieces of information that you are looking for in all of these problems. Number one, does it start in the positive or does it start in the negative? Number two, how high are the peaks? The height of the peaks. Number three, where is the center line? That tells you how much you've been shifted up or down. At this point, these are the three things that you're looking for. And you're looking for them in every single graph. Ooh, I should also say, as a preliminary measure, I'll use 0 for this one. As a preliminary measure, step 0, find out if it's a sine or a cosine graph. Find out if it starts at the origin or not. So, is it a sine or cosine graph? Is it a positive or negative sine or cosine graph? How high are the peaks, and what's the center line? The sine or cosine graph tells you whether or not it's a sine or a cosine graph. The positive or negative tells you whether or not you need a positive or a negative sign multiplied by your cosine. The height of the peaks tells you how much you're amplified by, how much you multiplied by. The center line tells you how much you shifted up or down. So that's just merely plussing by something or subtracting by something. But those are the bits of information that you're trying to find as you look at the problems. Let me do, just in light of this, because given that there was so much silence whenever I was asking questions, this must be something that's not well understood. And sine and cosine graphs are a rite of passage for a pre-calculus student. They are a rite of passage, and I will tell you why. Look at the nature of this. This goes forever, right? Can you think of anything? Can you think of anything that does something back and forth, back and forth, back and forth forever? Anything?
Heart
Just-
monitor, when they were just people's like left.
Heart monitors. You beat, you beat, you beat, you beat, you beat. Anything else? Like a wave. Waves in the water. Anything else?
Frequencies,
Like what do you mean by that?
like sound frequencies, like when it pops up.
Sound frequencies. Now we're getting really technical, yeah. Anything else? What if you put a little ball on a spring and went boing? Grandfather clock? Same principle. I'll tell you right now, if you get into a physics class and you try to model a grandfather clock, you need a sine wave to do it. And the grandfather clock would not have been created were it not for the sine wave. We call it the sine wave because it looks like waves. We can do that too, but it's sine wave. So that's what That's why I say it's important. That's why I want you to fully understand this, because this is at the heart of so much. This thing keeps pretty dang good time. How does it keep pretty dang good time? What about a watch? Is anybody in here wearing a watch? You've seen a watch before. How does it keep time? It's not plugged into the wall. There's a little tiny piece of quartz in that watch that is vibrating ever so slightly. And the little slight vibrations of that piece of quartz are telling the watch how much time it's elapsed. How do you measure the vibrations of the quartz versus the seconds that have elapsed? Can't do it without a sine wave. The watches that they're selling at Walmart for $1.50 could not have been made were it not for these. I mean, I'm giving it I'm making sine waves sound like the greatest creation in the history of mankind. And in some respects, they're fantastic, because so many things that we see every day rely on. Let's take this 0, 1, 2, 3 step. Isn't that a song? 1, 2, 3 step? Isn't there a song?
Yeah.
Yeah.
Yeah. Well, we have a 0, 1, 2, 3 step now. Okay.
This one.
This is our new song. Holla. Right. Okay. Let's look at 15. Let's look at 15 together with these new glasses. Like we have a new set of eyes to look at them. We have a new lens from which to look at the world. This goes up to 30. Center line at 5. Down to -20. Because I'm fully aware of the fact that you can go to the back of the book and get the answer for 15 really easily. And then you're like, okay, fine, done. But when these come up on the quiz and it's worth 16 points apiece, you're going to be like wanting to know how to do these problems. Because this is important, because we couldn't tell time without it. Oh my gosh, right? I'm putting so much on this. I'm like, my back is like getting heavy from the drama of this. You know what I mean? Maybe you're feeling the same thing. You're like, oh my gosh, this is so dramatic. These sine waves. Crazy, right? Crazy. Where we can go with these things. So, tell me I drew the right one. Yes, I did. 15. Now, step 0, sine or cosine? Cosine. Step 1, positive cosine or negative cosine? Positive. I like the thumbs up for positive. 2, height of peaks. How high are our peaks? 25. That's our multiplier. 3, center line. 5, positive 5, right? So basically, what we did is we took our cosine graph and we stretched it, but then we just went, picked it up 5, right? And how do you take all the values in your table and put them up 5? Just put a +5 at the end, right? I mean, it sounds so stupid, but that's the way that you do it, right? You got this big table of values. You need all these y values to be 5 more. You need everything to go up 5. Just add 5 to all of them, and you're done, right? It seems so silly, but that's what we do. Okay, so we put it all together. We got a positive cosine 25 times, and we add 5. So this is cosine, but it's positive, and it's multiplied by 25, and we add 5. There it is. If you walked in here today about these things at a 5, if you walked in here at a 5, I'm assuming that you walked in here at a 5, how do you feel now? At least a 7? Good. 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 Other questions? Because there was a section on sine and cosine waves that you guys covered with the sub, and I have a feeling that it made almost no sense. Well, you told me that for one, but, for two, given how silent it was when we were going through these questions, I have a feeling that what we did today is gonna pay a lot of dividends, and that makes me happy. Other questions? Okay, I'm gonna erase the board and then pick up your HW. Those are, jaw muscles of an ape, by the way, if you were curious. And these are the jaw muscles of the human.
Can you get animals helium?
Sure. Sure, I mean, you just have to like force them to inhale it, but, yeah, yeah.
Imagine an ape on like so.
Are you guys imagining giving your dog, you know? Yeah.
I look at my dog with sulfur.
You have like a little chair.
I know, people want to scare dogs, scare every dog.
Okay, let me pick up the homework.
Except I think the dog would die because I'm pretty sure we're gonna do a breathing exercise. Yes.
So remember what Erica said, name, date, section number, problem numbers. It's foolproof at that point.
Is it okay if we work like horizontally?
Oh yeah. Oh yeah, but work sequentially.
In order.
Sequentially. She would like,
How you would do that?
I mean, I'm not kidding you, there's a piece of paper sitting right here on the desk, or there was, that went 9, 10, 1 through 8. And it was like, yeah, what the heck? So I mean, I can, and if I'm being honest, like, in full disclosure, like, I don't care, but other people do. And other people care enough to throw those things away. So she's looking out for you. She's looking out for you. Like, I'm looking out for this, like, primarily. She's looking out for you for things beyond just this. Because, yeah, that, putting your name on that, putting the date, putting the lesson number is, yeah, that's just good practice. 51. By the way, good talk on sine waves today. We're gonna start notes, and this is gonna be the shortest day of notes that we've ever had in your life. You've ever had in your life. And we're gonna finish up what we start today, tomorrow. I'm just really glad we got that sine wave thing out of the way, because that was, you gotta feel better about that. I feel better about that. 51. Common and natural logarithms. We know what logarithms are. Remember the first time we saw logarithms? You guys are just like, ugh, right? Telling you they're useful. Bacterial growth and decay, you can't do it without logs. The common logarithm is base 10. The natural logarithm is base e. E is an irrational number like pi, 2.718, 2.71828, whoops, 2.7182881, it goes on forever. Why is E important? Calculus. You'll find out in a year. For now, just know that E is that number. Now, when we express common logarithms, if there is no base written and you write it logx, assume the base is 10. So, in here, we're going to assume the base is 10. For the natural logarithm, the French were actually the ones who perfected the equation that was necessary to derive the e. So they developed their own notation, ln, which stands for log naturel, right? This is all Francais. And if you write ln x, this is assumed to be a log with a base of E. Now, you have no way of knowing why E is special. All I can tell you is, when it comes to, in calculus, we pick up a couple new operations, like addition and subtraction. One of them is called the derivative, one's called the integral. E makes derivatives so easy. Think E for easy with derivatives. You'll be thankful when you see E in calculus. But for now, just leave it at that. I wish we could go into more detail about solving problems, but we just don't have enough time. But I'm perfectly happy with that, because what we did with those sine and cosine waves was huge. So, at this point, let me just send you with some homework so that you can get yourself even more comfortable with the things that we've recently discussed. Tomorrow, we'll pick up right here and answer your uncertainties, because this was the section that you said, we can do it, but we have no idea what's going on. So tomorrow, you'll still be able to do it, but you'll know what's going on. So that'll be good. 51. Take a look at 10, 11, 13, also take a look at 17, 18, 25, and this is going to be a flashback, but a good one. 27A, just A part. I'm also going to add 29, and that's it. 27A is going to be a flashback, but you'll enjoy it. It's a triangle problem. Oh, it's one of those Art Coast problems, but you'll enjoy it. You'll enjoy it. It'll be fun. It'll be good practice.
I did? Yeah, 'cause remember Lauren maybe.